March 2nd, 2016. At dawn on the Kazakhstan steppe, two identical twins stand face to face for the first time in a year, except now they are no longer truly identical. NASA's most ambitious experiment sent astronaut Scott Kelly into space for 340 days, while his twin Mark remained on Earth. When scientists compared them, the results defied everything we thought we knew about human biology. Scott's DNA had shifted, his telomeres, those markers of aging, grew longer in space, then crashed to record lows on return. The title isn't an exaggeration. One twin really did age differently than the other. But if space can reshape our very DNA, how far could these changes go for the future of humanity? The Soyuz hatch cracks open to the sharp wind of the Kazakh plain. Scott Kelly blinks against the morning light, muscles barely remembering gravity after 340 days in orbit. Recovery teams in orange parkas swarm the capsule, checking for fumes, then reach inside. They lift Scott out, careful and steady, placing him in a reclining chair next to the scorched metal shell. His hands tremble as he grips the armrests. Blood rushes to his head. The ground feels like it's tilting. A medic shines a flashlight in his eyes, asks him to follow a finger. Heart rate, blood pressure, temperature, all logged in rapid succession. Mark Kelly stands just outside the medical tent, bundled in a parka, watching his brother emerge from the spacecraft. The two haven't been in the same place since last spring. Mark looks unchanged, sturdy, grounded. Scott looks pale, drawn, a year older in ways no one can quite name. They lock eyes. Mark steps forward, pulls Scott into an awkward, wonderful hug. The cameras catch the moment. Two men with the same face, but one has just returned from the edge of human endurance. Inside the tent, doctors run Scott through balance tests. He tries to stand, wobbles, laughs it off. Mark sits beside him, acting as a baseline. Every vital sign, every reflex, every answer is measured against his twin. For the scientists, this is the perfect experiment. Control and subject side by side. For the brothers, it's something stranger. Mark's body stayed on Earth. Scott spent nearly a year in microgravity, bombarded by cosmic rays, eating freeze-dried meals, sleeping to the whir of air filters. Now their reunion is more than just a family moment. It's the first chapter in a story about what happens when you split a human in two, send one across the void, and bring him back to compare the results. Blood samples from Scott Kelly, drawn at regular intervals aboard the ISS, tell a story no one saw coming. Scientists at Colorado State and Weill Cornell run the numbers by qPCR and flow fish, expecting the usual signs of stress. Instead, they see Scott's telomeres, those protective caps at the ends of chromosomes, getting longer. Not by a little, by 14.5%. On Earth, Mark's telomeres barely budge. This is not how aging is supposed to work. In normal life, telomeres shrink with every cell division, worn down by stress, radiation, and time. Shorter telomeres mean older cells. In space, with cosmic rays and microgravity, the expectation was even faster erosion. But Scott's chromosomes are doing the opposite. Dr. Chris Mason, one of the study's geneticists, calls it the most unexpected result in the entire mission. The team checks for lab error, runs the assays again. The numbers hold. During months in orbit, Scott's telomeres stay stretched out as if the clock on his cells is running backward. No one can say for sure why. Maybe it's the strict diet, the daily exercise, or some unknown effect of microgravity. Maybe the body, under constant low-level threat, is flipping a survival switch no one has seen before. Then, within 48 hours of landing, the paradox reverses. Scott's telomeres crash, shrinking not just to baseline, but below it. 2 days after return, his cells show more critically short telomeres than before the mission. The rapid shortening leaves researchers staring at a puzzle. What does it mean to age in reverse, then snap forward? Is this resilience or a sign of hidden damage? The data leaves the door open. The next round of tests will dig deeper, but for now, the numbers refuse to give up their secret. Lab teams at Weill Cornell and Colorado State begin processing hundreds of blood and saliva samples from Scott and Mark. Machines hum through the night, sequencing RNA, scanning for methyl groups, mapping the ebb and flow of gene activity. The numbers come back with a pattern. About 93% of Scott's gene expression, thousands of genes flipping on and off in response to space, returns to normal within a few months on Earth. But the rest doesn't. 7% stays changed. Not just a statistical blip, but a real persistent divergence. These genes cluster around DNA repair, immune signaling, and bone metabolism, the core systems that keep a body stable under stress. Researchers run methylation profiles looking for chemical tags that silence or activate genes. Scott's white blood cells show new methylation patterns, especially near immune genes. Most fade after landing, but some remain like a watermark from space. It's not a single mutation or a catastrophic DNA break. It's a subtle, lasting rewrite in how the body manages damage, infection, and bone renewal. The immune system throws another curveball. During the mission, Scott receives a flu vaccine. His body produces antibodies just like Mark's, but the molecular signature is different. Cytokine levels, tiny proteins that rally immune cells, spike in Scott, forming a pattern never seen in terrestrial responses. After landing, his cytokine profile takes months to settle, with some markers still out of range half a year later. The data hints at a new immune baseline tuned by months in microgravity and cosmic radiation. The research teams debate what it means. Is this adaptation or a warning sign? The lasting gene changes don't point to superpowers or disaster, but to a new normal. For Scott, the experiment doesn't end at touchdown. For NASA, the message is clear. Space doesn't just stress the body, it leaves a molecular fingerprint that doesn't fully wash away. A year in orbit strips the body to its essentials. Scott Kelly's skeleton, once as dense as Mark's, comes home lighter. Decades of data say astronauts lose up to 1 to 2% of bone mass per month in microgravity. For Scott, the DEXA scans confirm the trend. The hip and spine show measurable loss. Recovery takes months, sometimes years, and older astronauts may never get it all back. Meanwhile, the carotid arteries thicken, a warning sign for stroke on Earth. The retina swells, vision blurs, blood pools in the head. These are not just temporary annoyances, they're signs that human anatomy is bending to a new environment. Cognition slows too, reaction times stretch by fractions of a second. On the ISS, Scott's mind stays sharp enough to run experiments and dodge emergencies, but after landing, speed and accuracy drop. NASA's cognitive battery shows mild lag, especially in the first weeks back. It's not dramatic, but it's real. Some functions rebound, others don't. For long-haul missions, even small slips could mean disaster. Gene expression data hints at something deeper. 7% of Scott's gene activity, especially in DNA repair and bone metabolism, stays altered for months. The immune system, already running on a different playbook, may never fully reset. This is adaptation, but it's also divergence. Bioethicists call meetings. If 1 year in space can change a twin's biology, what happens after a generation on Mars? How many cycles before the changes stick? The word speciation comes up. Once a thought experiment, now a real debate in NASA hallways and university labs. Some researchers push for gene editing, arguing future settlers will need better tools to survive radiation and bone loss. Others warn of unknown risks. There's no NASA policy for screening or engineering astronauts, yet. But the Kelly twins are now the first case study in a question that won't go away. How long before space travelers are no longer just Earthlings in exile, but something new? The line between adaptation and transformation is getting harder to draw. Scott Kelly's year in space led to a 14.5% increase in his telomere length, followed by a rapid drop below baseline just days after his return, an effect never seen before in identical twins. NASA's twin study revealed that while 93% of Scott's gene activity returned to normal within 6 months, about 7% of his genes, connected to immune response, DNA repair, and bone formation, remained altered. Bone density in Scott's hip fell by 5%, and his cognitive reaction time lagged by 10% compared to his brother Mark. Yet, the long-term health impacts of these changes and whether they could accumulate on future missions remain unknown. Today, no NASA policy requires genomic screening for astronauts, and many of the molecular mechanisms behind these shifts are still under investigation. The Kelly twins' story stands as documented evidence. Human biology can diverge dramatically in space, raising urgent questions about the future of astronauts, and perhaps the very definition of what it means to be human.